Action.
Okay, so now I'm going to describe our latest approach to designing this type of element. So here is the concept. So the idea is to define a volume, okay, which is described by the index of refraction. Okay? And if you look at this theory of scattering from, for example, Parnell walls, you get these formulas. So the idea is that here you can think of a piece of glass with changing index of refraction inside it. And this is called the scattering potential. Okay, it's the index of refraction square is a function of 3D minus 1. So this is the index contrast. If you had it in other than vacuum or air outside, this would be N0. So you have that, and we want to describe anything that is scattered from that volume, which is, and then design this, okay? Not just analyze it, but make some, specify what is this n squared, okay? This function in 3D. Now, according to this theory of scattering, if you make a 3D Fourier transform now, okay, the same Fourier transform, but now three-dimensional, you get another volume. So this is a k-space, or so you have kz, ky, and kx normal to the screen. And so far I didn't pose the wave equation. If you pose the wave equation onto that, we're going to see that we're going to get these spheres, okay? And this sphere is called the Ewald sphere. And anything that is satisfies the wave equation has to be on that sphere in Fourier space. So even though you can generate whatever you want here, you can sculpture this index of refraction as much as you want. But on this side, you're always going to be on this Ewald sphere. And this Ewald sphere is defined as follows. This is the origin of the 3D k-space. And this k minus k in is if you illuminate this volume with a plane wave of wave vector k in, here the center of the sphere is located as minus k in from the origin. Okay? So you get this sphere. Now, half of this sphere is the transmitted wave, and half of this sphere is a reflected wave. So you can also shape things on reflection. Okay, so there is going to be forward scattering, back scattering, and those are the two halves of that sphere. Okay, so all that is from the 3D Fourier transform. Only a sphere is satisfied. Your domain is going to be on a sphere because of the wave equation. Then you unwrap that sphere, and you can get the far field for the forward transmitted wave and the reflected wave. And you can look into any direction, not only along the Z, you can look at any angle like that. So that comes from the theory of scattering. So that's how we analyze. Now the basic assumption in this formalism here is that we have weakly scattering, meaning that every wave is only scattered once. Okay? So weakly scattering, strongly scattering is more complicated. So let's keep it simple. So in this case, we impose, again, to design the CU logo, okay, and we, well, nice, here, we design a structure that gives you CU, and these are two simulations. This is using the same volume diffraction, and this is using beam propagation method, which is totally different method, where we go layer by layer, and to show that this was a confirmation before we did the experiments that this works. But you can work in the computer and get things that are wrong. So this shows that it's okay. So again, as you can see, it's different than in the thinner hologram. This is an amplitude, quote unquote, volume hologram, but you don't get the full twin image here. Okay? And that's because of the volume character. And you can eliminate this also. If we have time, I'm going to talk about that. Now, one of the things we can do is eliminate this volume on different directions, so you get different equal spheres. So if you illuminate along the z-axis, you get this sphere. If you illuminate along this axis, you get a different sphere. So each sphere corresponds to different plane wave illumination. And now you can make that design in such a way that, for example, you're imposing on this sphere one pattern, on this sphere another pattern, on this sphere another pattern. And so when you illuminate that volume along the z direction, you get this in the far field. When you illuminate in this direction, you get this. When you illuminate in this direction, you get that. So you can have, this is called angular multiplexing. And this can be done using this volume optics. So here is a simulation of a specific design that does exactly that. Again, we have C, U again, but either C or U. So if you illuminate normal, you get C. If you illuminate at some angle, you get U. And in the middle, you get AC. So this is the simulation for green light. And look at the number of boxes, 64 by 64 by 64. So think of the problem, calculating 3D Fourier transform takes a longer time. But still we could do it better. But also fabricating these things point by point takes time. So we start with very low number of pixels or boxes. And this is what we call this volumetric space bandwidth product. You know, space bandwidth product is essentially the number of pixels, but here is the volumetric version of that. Okay, so now how do we do this calculation? We use again these projection algorithms, similar to Gesper-Saxon. We start with a volume, and then make a Fourier transform, and then on each sphere we impose different patterns. We change the Fourier transform on those positions to your required pattern, similar to what you do when you do a diffractive elements calculation. Then you apply the new amplitudes, reinforce, reduce the background, then perform an inverse. Oh, sorry, you put this back on the Newell sphere, inverse Fourier transform in 3D, and you get a different volume, but this volume might have, for example, huge changes in index that are impossible to achieve in practice. Or you could have, for example, we want to make binary index of refraction, you could have losses or all kinds of things, because it's going to be a complex number. And this complex number, if it's the imaginary part, corresponds to losses. So you now want to have a binary phase volume here, so you again impose this constraint, so you find the closest thing to this, but has binary phase, and then you iterate. Okay? So it's a projection, similar to Gesper-Saxon, but in 3 dimensions. And in multiple domains, because we have different equal spheres. And interestingly, you get a maximum, in one iteration you almost get there. Okay? You get very quickly to something close to the result. This is the diffraction efficiency here, increasing afterwards slowly. This is calculated with the mean propagation method. This is with volume diffraction. And the mean square error also. You get, in the first iteration, great improvement, and then slowly asymptotic. And you can see you don't get to 0. You don't get to 0 because with this number of pixels, and it might be impossible to do it to 0, but you get pretty close. Another thing is the index contrast, because we assume it's weakly scattering. So once we have a given design, we can simulate for different index contrasts using mean propagation. And if you have a very high index contrast, it doesn't work because it's not what you design. And if you have a low index contrast, it works. And then you want to find the right index contrast that will give you the highest diffraction efficiency. And the diffraction efficiency is not that great, but it's better than what you get with the binary hologram, thin binary hologram. It's between 10 and 15% in theory, and here we have for C and U for each of the 2 patterns. Okay, so the diffraction efficiency can be controlled by the index contrast. And This is the first experiment of this volume optics. So here we have, again, we use the femtosecond laser in glass. This is a DSC image of the front face. This is a representation of the index modulation. And these are cross sections of this along YZ, XZ, YX. Okay, so you see it's not periodic, but it's a volume because it has 64 by 64 by 64 voxels. And here you have, if you come with 0 degree, you get the C. You come at 15 degrees, you get the U, and in the middle, you don't get anything. So this is one of the things you can do. You can do for different angles, different functions. Again, you can do this with a regular holography, but this is a different type of encoding, so it opens the door to other designs that are, in fact, when you do diffractive optics, you can show that things that are done with diffractive optics can have better efficiency than if you do it with holographic recording. Another interesting thing is the near field. What's going on in the near field? So this is here. This is the volume, okay? Along. So this is Z and Y, okay? And you have the volume here. So for the light coming at 0 degree, that gives you C. You see how the waves are built up inside the volume. Okay? So it's not that everything happens on one plane, as we saw before. These waves are built up. And here you see something that looks like a sinusoidal variation. And that's the reason, because then you get the symmetric C here. And that's giving you the sinusoidal variation. Now if you come now at an angle or rotate the volume, that's shown here, you see the waves look totally different. Okay? And again, here you get something that this is a near field. In the far field, it's going to give you the U. But here you see the U is not symmetric, and that's why here you don't get this contrast that you get here. It's mostly like a linear phase that is going to generate the U in the far. So this is interesting because in the future we think we could design the near field with this volume optics, and that would be something of interest for example, for plasmonics, when you want to excite different types of plasma and so on. So what can you do with the color? So here we have again, when you have different colors, you get different equal spheres, but they have different size, because the K has different size. K is pi over lambda magnitude. So for the blue, you get this sphere, for the green, a bigger sphere. And for the red, I think it should be the opposite, right? The colors don't correspond to the colors. Okay, so shorter wavelengths give you longer, give you bigger spheres, longer wavelengths give you shorter, smaller spheres. And again, now you can put different patterns of the sphere, okay, that corresponds to different color. And you could combine angular multiplexing with frequency multiplexing. There's no reason why this blue sphere could not be down here, and then you have a combination. That was what I was referring earlier today, that you could combine angular frequency and different three-dimensional functions. And this is a simulation result, where you get the C and the U. This is for 800, this is for far 58. These wavelengths are just the lasers we have handy, okay? And they are far apart. The reason they need to be far apart is because of the number of pixels we have. Again, it's very low, 64 by 64. And this is again the representation and the experimental results. By the way, all these are experiments, okay? So here we got all the three wavelengths normal to this phase. But you get C with the blue and U with the infrared, with the near infrared, and these are different cross sections of that volume. So this shows that you can do these are the first demonstration of the computer-generated volume optics, where you can do both angular and frequency multiplexing. And again, the near field is interesting. In the near field here, we see that the waves are going up for the blue, because the C is up here, and here they are going mostly down for the, sorry, up for the C, down for the red, and the blue because they are down here. So the near field also can be shaped with the different colors. So to give you a historical perspective, because my motivation is very ambitious here, because I'm saying I can do high index contrast, low index contrast, time, spectral shaping, and so on. But these demonstrations are just toy results. Again, they have 64 by 64 pixels. It's like if now I would offer you an SLN with 64 by 64 pixels. So, well, if you look at the first paper on holography, we see that they use M square, that is 64 square, okay? But this was in 2D, and now we can buy SLMs that, or fabricate multi-megapixels. So I hope with time we will come up with ways of making high volumetric space boundaries product volume optics. And also, if you look at a similar related area, which is digital holography, where you record a hologram with a CCD camera or with electronically. And then if you look at the first digital holography experiment in '67, about the same year, you have a race of 256 by 256. It took 5 minutes to calculate the Fourier transform, and they had 52K of memory in the computer. Okay, so hopefully before we won't need to wait 50 years or 40 years to see how this volume optics take shape, but this is our recent paper on this that shows this result. So I expect this, in fact we are going to continue working on these lines, but as I said, you can have different, you're using more dimensions to control light in multiple dimensions, and that's what you need. And for example, you could try to control the coherence function in 3 dimensions, or shape pulses, as I said, or encode multiple point-spread functions in one single element, and so on. So there is a lot of work ahead in this area, but I hope it's going to be useful at some point. So what I showed now in the afternoon is 3D optical functions to control optical tweezers and to track particles, trap. PSF engineering we saw yesterday for imaging and super resolution. So volume optics maximize the control of space-time frequency polarization. We showed control of polarization and the coherence function. This is what I think is the first demonstration of 3D aperiodic volume optics. I emphasize that it's aperiodic because if it was periodic, it would be a photonic crystal or something like that, which has been widely studied. I think the interesting thing again is when you break the periodicity. And future applications, as I said, space-time control, spectral imaging, for example, computational sensing, and so on. So again, this was work at the beginning mostly done by Wenjian Kei, who graduated. Tim Gerke has done the last work on in this area with the help of Ariel Liberton. Ethan is now at Harvard. He did the first work on optical tweezers and the latest work on optical tweezers. And as usual, we try to work as a team, so we get help from all of the other students and postdocs. And I would like to also acknowledge things I've done. Joseph Shamir was my advisor at the Technion several years ago. And Boris Spector was a collaborator also. Yoav Shechner was back then a student, now he's a professor also at Technion in Israel. Eric Miller, with whom I did these femtosecond experiments. And then Miles Budget, we have some collaboration at Ivan lately and sources of support. Thank you, and you're free. Remember 4:30 a.m. Semi-finals World Cup. And I have to, for full disclosure, I'm from Uruguay. So you know who you need to root for. And if you don't see me tomorrow, you can correlate.
I have a question. How long does it take to actually fabricate one of these devices?
So, order 1 hour again.
Only 1 hour?
Yeah. But again, it depends on how many pixels you have. But my proof of concept is DVDs. Okay? DVDs is a point-by-point, essentially, fabrication storage, and they are pretty fast. So there's no reason why, if optimized and mass-produced a specialized machine to do this, it could be done faster. Now, we're also looking at other ways of doing it with lithography in parallel, layer by layer. So we'll see. That's what maybe from next conference I have something to do.
And are there prospects for copy them? I always thought that the great virtue of two-dimensional holograms and three-dimensional.
Yes, well, if you do layer by layer, and we know that from Pentium has 64 layers. Last time I know. So 64 layers can be done with lithography, and we know that Pentiums are replicated with high accuracy. So there's no reason why this couldn't be done. You need a good motivation. Okay, so but I think there are techniques, and further specialized for these volume elements. I think it's good. Yes.
Do you have any ideas of applications for your multiplexing?
Yes. So as I said, one thing we are interested in computational optical imaging. So I showed yesterday you can make this face mask. So now with this you could make a face mask, a different face mask for different spectral lines, for example. So you could do spectral filtering, spectral spatial filtering, for example. And I talk about shaping femtosecond pulses for different applications, quantum computer. I also talk about anti-counterfeiting. If you make this, we have a unique way of encoding information, more robust than the holograms that some of the money do.
I guess as a frivolous thing, you could perhaps also do family photos as well.
Sure.
Because if you have red, green, and blue,
Yes.
say you could create a combination of red, green, blue, such that you could approximate all the other colors, like a LCD screen or something, except
Yes.
you use a 3D hologram to do it.
I haven't talked about that, but one could dream of having a 3D SLM.
Mm.
And I don't think it's impossible. Just again, somebody must have a good motivation to do it. So I think if with these toy experiments, eventually we're going to show with enough potential commercial applications that somebody's going to invest money in do something bigger, right? As I say, you could use a technology that's used for a Pentium, but it's expensive. So there is enough interest. I think it's not something that is impossible within the reach. It will be expensive. Okay?
Any other questions? Okay, now let's thank Rafael and Parnell.